we talked about Euler-Lagrange equations, which is d dt of dl dq dot minus dl dq equals q, and then I just put a suffix j, where the L is the Lagrangian, right? And for Lagrangian, we saw that it is basically the kinetic energy minus potential energy. We wrote down the kinetic potential energy for a ball, and am I clear now? I just saw the chat, there was an echo. Is there an echo still?
Yeah.
Okay, my bad. I have to mute the other computer. Is it better now? Okay, perfect. I'm sorry about that. So in last class, we talked about Euler-Lagrange equations, where I wrote down the Euler-Lagrange equation. L is the Lagrangian. It's the kinetic minus the potential energy T minus V. And for the projectile motion, we were actually able to write the sort of find the equation analytically. It was simple enough. But what happens is when you look at more complex systems, like in fact, double pendulum, which we'll be talking about in the next class, you'll see that the Lagrange is pretty complex. And if you try to find the Euler-Lagrange equations, is a good chance that you will make some mistakes. So it's important that we are able to sort of automate the process, or use a computer to do this calculations. So this class is going to be focused on using symbolic derivations of equations. So let me write this down. May be too complex to be amenable for hand derivation. So this motivates using Matlab for derivations or symbolic derivations. Okay, so that's what's going to be the focus of today's class: symbolic derivations. Okay, so what I'll do is I'll basically put down a few things on paper, and then I'll write code which will do exactly what I'm going to write down. Okay, so let's say that we want to find the derivative of an expression like this: f0 equals x square plus 2x plus 1. Okay, really simple. If you take the derivative of f with respect to x, and this is the complete derivative, so it's t and not partial, equals 2x plus 1. Okay, sometimes you need to find the value of df dx at x equal, let's say, 1. Okay, then you can see that it's simply 2 times 1 plus 1, which is 3. Okay, now how do you use Matlab to do this? So this is hand calculation. Okay, with Matlab, okay, you can actually define symbolic. So before you use, by default, as we've realized, we need to define values with numbers. So for example, I need to define x equals 1, x equals 2, otherwise Matlab will complain. But if you want to do symbolic derivation, then you first need to define that these variables are symbolic. So you'll define x to be symbolic, and then you need to put this term real. And that's just because if you don't put it, it will treat x to be a complex number, and you start getting i's and j's in your equations, which you don't want. So this is how you start. Then you define f just like it is defined here, x squared plus 2x plus 1. Okay. Then if you want to differentiate an expression, there's a command called diff. So in that case, I'll call it df dx equals diff f comma x. So this is taking the derivative of f0 with respect to x. And then if you want to find the value of df dx at a particular value of x, then there's a command called subs. So subs df0 dx. So I want to put in df dx at x equals 1. So I'll put 1. Okay. And my claim is that this code here on the right side will do exactly what I did with hand calculations. Okay. I'll write the code in just a bit, but before that, let me tell you something a little bit more than just finding the derivative. Sometimes you need to find the numerical derivative. So this is the symbolic derivative. Sim derivative. Sometimes you want to find the what is known as the numerical derivative, which is you do not quite use the sims command to do it, but you just use the definition for derivative to find the derivative. So what I mean by that is, let's say, so numerical derivative. So in this case, I need to find df dx at x equals 1, but I do not want to actually write the expression for df dx in closed form like I wrote down. I differentiated that symbolically. So how do you do that? So what you can do is, we know that the definition of df dx is basically f, we call that f1 minus f0 divided by x1 minus x0. What's happening here is this formula is basically, so this is x0 at which I want to find the derivative. I'm basically finding the value of, so this is f, this is point x1. So I'm finding the value of the curve at x0. I'm finding the value of the curve at x1, so f1. And then I'm just using the definition of df dx in this way, f1 minus f0, which is basically the y value or f value difference divided by the difference x value. And this will work if you do a small perturbation. So x1 should be very close to x0. Okay, there was a question. Did I do a mistake? Let's see. Yeah, my bad. This should not be 2x plus. So derivative of x squared is 2x and derivative of 2x is 2. So thanks for correcting me. So this will be 2x plus 2, and so this will be 4. And the other side will remain same. Thanks for correcting me on that. Okay. So I could also use this numerical derivative to find df dx, and this is going to be useful not now, but later on when we talk about modeling Legate systems, finding derivative this way will be very useful. So I'm also going to write the code which will find the numerical derivative. So this way of finding the derivative is known as the forward difference, or this formula is the forward difference formula. There's another way, which is, so this is actually not as accurate as another way of doing it called as the central difference. So in the central difference, you have x, x1, or x2, x1. And then you find the value here, f2, f0, f1. You actually don't need the value of f0. You only need two values of f2 and f1. So then you find df0 dx equals f2 minus f1 divided by x2 minus x1. Okay, again, x2 and x1 are sufficiently close to x0. Central difference more accurate than forward difference. Okay, so what does it mean to be sufficiently close? What I suggest is take x2 to be something like x0 plus 1e negative 4 or 1e negative 5. Okay, that's what I mean by close. So x2 will be that. Since it's a positive value here, x1 will be x0 minus 1e negative 5. You don't have to take the right and left perturbations to be the same. You can actually take a different value if you want. You can take that to be negative 6. It won't really matter. Okay, it's usually a good practice to take the same difference. Here also x1 should be x0 plus, let's say, e raised to negative 4. And there is more things about what's a good perturbation, and that's really not going to be the focus, but the perturbation depends on what is known as a truncation error, and then there is the round off error, which is kind of important when you do this difference. I would not spend too much time talking about this, but you should be mindful that you just can't take arbitrary small uh, perturbations. If you take 10 raised to negative 12, that will not work because your machine is accurate to about 12 decimal places. So you'll essentially get noise. Okay, so next what I'm going to do is I'm going to try to write MATLAB code, which will do both these things, do the symbolic calculations as well as the numeric calculations, and we'll see if it conforms with what we did by hand calculations. So when we did hand calculations, we saw that the value for df dx at x equals 1 was 4, and that's what we're trying to get. Okay. Let me know if you have questions. I'm going to shift computers. Let's start. Let's first do the symbolic calculation. So first of all, I'll do CLC and clear all. I don't need to do close all because I'm not going to generate any figures here. So symbolic differentiation. Okay, so sims x real, f0 was x squared minus or plus 2x plus 1. df0 dx is diff f0 with respect to x. So if you run this, we save this as example symbolic diff. Okay, so what we expected was 2x plus 2, which is the derivative of x squared plus 2x plus 1. If you did not put sims x, then what happened is it'll say unrecognized symbol because it expects x to be some value. It can be either a numeric value or symbolic value. Okay. Now, if you want to find the value of f df dx at x equals 1, then what we need to do is I'm going to put x val equals 1. I don't want to use x because I already used it for symbolic variable as a symbolic variable. The command which is used to find the value of any function at a particular value is called subs. So df dx at x val. So if you run this, we'll expect that when you take the derivative of this x squared plus 2x plus 1, you should get 2x plus 2, and so x equals 1, we'll have 4. So the answer is 4. Okay, so that's super easy to do with Matlab, the symbolic derivations. In fact, when we'll see later on, it can do very complex calculations too. Let's try to do the other part, which is finding the numerical, using numerical differentiation to find the derivative of f0 at x equals 1. So clear all numeric differentiation. Again, sims x real. Sorry, I don't need sims x because I'm not really using symbolic toolbox. So f0 equals, so I need to define a function f equals fun x, where f equals x square plus 2x plus 1. Okay, and since this is going to be a function and I need to define this first thing as a function too, I cannot define it as a script. So let me call this as function example def num. Okay, and then when I save it, it automatically gives me the same name. Okay, so I define f. If you want to check it giving you the right value, let's try x equals 0. So if you put this and you run this, then when you put x equals 0, you should see the answer output should be 1. So when you run that, you get 1, which means it's working. Okay, so let's now find the numerical derivative. So we want to find the numerical derivative of x value equals 1. Okay, so first what we'll do is we'll find the value using forward difference. Okay, so forward difference, I need to define just two values. One is at, say, f1 equals subs f at x. Sorry, this should be fun at x. Okay, let me do it this way. In fact, a bit better, easier to understand. Fun at x val. Right, so this is finding the value of f at x equals 1, and then f0 equals fun. This is f0, f1 equals the value at x val plus, so a perturbation. So in this case, let me choose 1e negative 5. Okay, so always go ahead to check if it's doing what you intend to do. So I just ran this, it gave me f, and you see it's 4.000. Actually, there are more decimal places which you don't see. If you want to see all the decimal places, then you need to type format long. Now it will print about 12 decimal places. So you see it's actually 0004, so on. Okay, so now we are ready to use the forward difference formula. So we have df0 dx equals f1 minus f0 divided by 1e negative 5. So you can see that the answer is 4, what we expected from taking the derivative of x squared plus 2x plus 1 at x equals 1. Right, this is what we also got when we did hand calculations. You can see that it's not quite 1, it's actually 0.0001, which means that it's accurate to 4 decimal places. So that's the problem with using numerical differentiation. It gives you approximate answer. You could argue that this is not accurate because when you look at the 6 decimal place, actually there's a 1 there. let's try to do it by central difference and see if it's much accurate than the forward difference. So let's define f2 equals, so it's always a good idea to define this perturbation as a separate variable, because then I can keep reusing it. So let's say f1 equals x val minus pert, and fun x val minus pert, and then f2 equals fun x val plus pert. So this is just defining the 2 points I showed in my derivation. And then df0 dx equals f2 minus f1. Okay, in this case, it's going to be 2 times pert, because the difference between the input values xval plus pert minus xval minus pert is going to be 2 times pert. So let's evaluate this, and we see that now we have a value which is 4 times 1 in. So this is very close to 0, right? This doesn't have the 1 in the 5th decimal place. This is more accurate than this one. So that's central difference per u, which is much more accurate than forward difference. This is true for this example. If you try more complex example, you might see that central difference actually doesn't work quite well as you would expect it. So it's really more or less trial and error for different functions. So what we will do is we'll see how the perturbation affects this. Before that, let me define pert as 1e negative 5, and that way I can just change it. I don't need to define it here. Okay, so now we can actually start looking at how these things change as I change the perturbation. So this is a smaller perturbation. You can see that the values are almost the same. Of course, central difference doing slightly better than forward difference. Try 3, not bad. 2. Okay, now it's starting getting less accurate. So now we can see that the forward difference actually is doing much better than the central difference, but it's still in error. So this is what you'll get when you start increasing the perturbation size. If you want to go on the other spectrum or the other end, try -8, and then -11. So both look good. 12. And then I think this will give you garbage values. Okay, it still looks good, but it's getting less accurate. Okay, so I'll stop here, but you should try this with more complex examples to see how these two do. So again, there's no hard and fast rule on the accuracy, but you can expect that central difference to do a little better than forward difference. Just 2 into pert needs to be in parentheses. I don't think so. I mean, we can check it out. Or I believe this might be for this perturbation. Yeah, so that, that's strange. So this, I didn't expect this to affect. Right. So good catch. So it needs to be in brackets. That way, now you can see these values of, in fact, forward central difference is always better than forward difference. So good catch on that. Okay, any questions on this? No questions? Okay, so what I'll do is I have a poll here. I'm just trying to assess if how you guys are doing on the homework in terms of time spent, so that I can accordingly adjust the homework. Where's my poll? Okay, here it is. So I'm going to launch the poll, and you should, it's anonymous. I don't know who's putting what, but answer the poll, and then we can compile the results. Do you see the poll? Okay, I'm seeing people are replying to the poll. I'm going to motivate it with examples. So we looked at how to differentiate f, where f was a function of x, and we found df dx. But what if we were told to find the derivative of a function f, let me call it f1, where it's not just a function of x, but that x is in turn a function of t. Okay, then how do you find, if this is true, then find df1 dt, right? And the way I like to think about this is that f1 is a function of x, which in turn is a function of t. And so if you want to find df dt, then you need to, so we need to do this calculation, but we need to go through x, which then goes to t, right? And so if you want to do this, you need to use what is known as the chain rule, which states that df1 dt is df dx dx dt. Okay, this is the chain rule. So it is used to find the derivative of implicit functions. Okay, so example. Let's say that f1 is sine of x of t. Okay, so how do we find df1 dt? So it's df1 dx dx dt. So when you take the first part, which is df1 dx, you treat x as x, don't worry about t. And the second part, dx dt, takes care of the fact that x is actually a function of t. So this is going to be df dx1, which is the derivative of f1 with respect to x, is going to be cosine of x. And then the second part is simply dx dt, or some people like to put x dot. X dot is dx dt. Okay, so that's simple. Let's try to make it slightly more complex now. What if f or f2 was a function of x of t and x dot of t, where x dot, so then find df2 dt, where x dot is dx dt. So again, the way I like to think about this is there's f2, which is a function of x, x dot, and then that x and x dot is a function of t. So we want to find the derivative of f2 with respect to t, but in order to do so, we need to go through both variables. So we need to go from f2 to x, and then from x to t, but we also need to go from f2 to x dot, and then x dot to t. And so the way this is handled is we would have, instead of having one equation like here, or one part, we'll have two parts to it. And that's written like this: df2 dt equals df2 dx dx dt. So that's the first part, taking care of the first variable. So that's the, you can call the blue arrow. And then we have df2 dx dot. Okay, note it's dx dot because that's the second variable, times dx dot dt. So that's the blue part, and that's the green part. So I think this pictorial representation is really a powerful way of figuring out the chain rule and then eventually finding the derivative. Okay, so let's do an example, and then that will be the end of today's class. So the example is, find if f2 is x of t, x dot of t, find df2 dt. Okay, so let me write the formula. df2 dt is equals df2 dx dx dt plus df2 dx dot dt. So df 2 dx is going to be, so this is a derivative of f2 with respect to x. So when you do that, you need to take x dot as constant. So we'll have x dot of t times dx dt plus the derivative of f2 with respect to x dot. So here x is constant, but x2 is variable. So we'll have x of t. And then the second term remains the same. And then one step away from finishing this, x dot times this thing is simply x dot plus x, the first term, and second term is x double dot. So the final answer is df2 dt equals x dot square plus x times x double dot. So that's the answer. Okay, so next time I will show you how to take this, write it in Matlab to do the symbolic derivation. We did something very simple with a derivative. So there's a command called diff, and we used that to do differentiation of simple functions. Then we went a step further. We went to the chain rule, which is if you want to find the derivative of f1 with respect to time t, where x, so f1 is related to x and x is related to t, then you need to use the chain rule. So the best way of thinking about this is to write this particular visualization. So if you want to go from f1 to t, which is the red arrow, then you go via x, and so it's df1 dx dx dt. The second example we did was, now there's a function f2 which is a function of x and x dot. So if you look at the visualization, you have f2 goes to t through x and x dot. So to find that derivative, you need to take partial derivative of f2 with respect to x and f2 with respect to x dot. And if you do that, then for the simple example, we got for f2 equals x times x dot, we got this answer. So let's try to do this with Matlab first and see what we get, and basically check if we get what we get from doing a hand calculation. And then we'll extend it to do it for the derivation of equations of motion using Euler-Lagrange. So open Matlab. Let's make a new script. Okay. Okay, so CLC clear all. Okay, remember that F1 was, okay, before we, okay, let me just define F1. F1 was cosine of x. Okay, and we need to find the derivative of cosine of x, where it's x of t. And we want to find df1 dt. So that's going to be, is that right? Let me just check. Maybe, let's see. Was this the example we solved? Yeah, it was sine of x of t, my bad. So sine of x of t. Okay, so then I'm going to write f1 equals sine of x. I can't quite write x of t, but there's an implicit differentiation which I'm going to write down here. So that is going to be diff f1 with respect to x times x dot. Right? X dot is dx dt. X dot is dx dt. So if I run this, then it's going to be an error because I've not defined x and x dot. So I need to first define symbolic variables. So sims x dot, and I put real because I don't want them to be represented as complex numbers. So if I run this, we uncomment this. We save this as example chain. Okay, so we get x dot times cosine of x, and if you check, that's exactly what we had from hand calculations. Let's do the second one quickly. F2 equals x times x dot. So that was my equation. So I'll write F2 equals x times x dot. And now the chain rule says that I need to do diff F2 with respect to x times x dot plus diff F2 with respect to x dot times the derivative of x dot, which is x double dot. So I have not defined this variable yet, so I better define it here, x data. Okay, and then let's run this. Okay, so now this is the answer I'm looking for. It's x dot square plus x times x dot double dot. And if you check F2, you see that's exactly the same, x dot square plus x times x double dot. So here we were able to use the chain rule successfully in Matlab. Okay, now let's get back to the problem at hand, which was trying to derive the equations of motion of the projectile using a computer. Okay, so let me shift computers. From 2 classes back, I wrote down the formula for the Lagrangian, and then I need to use the Euler-Lagrange equation, right? So I'm going to basically copy this up, this Lagrangian formula. So it's 0.5 m times velocity minus mgy. Back to Euler-Lagrange, and in particular we'll do derivation or symbolic derivation of projectile equations. Okay, so as I said, the Lagrangian was half m times x dot square plus y dot square minus mgy. Okay, so the Euler-Lagrange equation looks like this. d dt of dl dq dot minus dl dq equals q, where q in this case is going to be x and y. So what I'm going to do is I'm going to write this down, write down the formula for dl dq dot and ddt of dl dq dot in the way in which I'll put it in Matlab. And I thought I should write it down because I think it still may not be very clear of how to use the chain rule. So first thing to note is that the Lagrangian is a function of x dot, y dot, which in turn is a function of t. Okay. So when I need to take the derivative of L with respect to t, I need to go via x, then x dot, and then y and y dot. Okay, so this the part which is the most hard for people to understand is the ddt part. Okay, the first two parts are easy. So that those are essentially, if you want to write dl dq dot, that's simply going to be diff of L with respect to q dot. Okay, and q dot is in this case either x dot or y dot. So that's easy. The second part, dl dq, is diff L q. That's also easy. So the hard part is d dt of dl dq dot. So how do we get this? So let's say that this term, I'll call that dl dq dot. Okay, because Matlab will not let me write it the way it is written here. So let me call it dl dq dot. So when I want to find this term, d dt of dq dot, what I would do is I would write it as, so it's going to be d dx dl dq dot times x dot. So I'm using the first one now. Then I need to go d dx dot dl dq dot times x double dot. So that's the second part. So that's just completing the first two. I still need to do the same thing for y. dl dq dot y dot plus d dy dot dl dq dot y double dot. Okay, so there are four terms here, not just two, like we had for the example I typed in Matlab. So we need to write this term as four terms through the chain rule. So this is the chain rule. Okay, so what remains to be done now is to take this, put it in Matlab, derive the equations, and check if these values match up with so the equations match up with the equations I got through hand calculations. So let me just do that. Any questions? I'm going to shift computers. Okay, so CLC clear all and close all. And let me call this examples derive projectile. Okay, so I'm going to write this code in such a way that you can relate it to the algorithm I talked about. Is essentially starts off with writing down formulas for position, velocity, find the Lagrangian, and then do the Euler-Lagrange. So let's just do it that way. So before that, we need to define symbolic variables. And those would be the position, the velocity, and the acceleration. Okay. We also need to define the parameters of the projectile problem. So this would be the mass, gravity, drag force. Okay, now we'll do it step by step. So the first step is position and velocity. So there's nothing really to be done here because position x and y and x dot and y dot are already defined. Okay. Later on, when we do the pendulum, we'll see that x and y are something we need to write by using some of the things we learned in previous classes when we talked about kinematics. So right now we don't have too much. The second step is write the kinetic, potential, energy, and hence Lagrangian. So this is basically copy paste from the notes. The kinetic energy is 0.5 times mass times velocity square, which is x dot square plus y dot square. Okay. The potential energy is V, is mass times gravity times height. And then the Lagrangian is the kinetic energy minus potential energy. Okay, so that's step two. The last step is, third one is Euler-Lagrange. You can refer to the notes, but let me just write it down here. D dt of dl dq dot minus dl dq equals q. Okay, so what I'm going to try to do now is take the formula I wrote down on paper and transfer it onto the computer. Since there are two variables, x and y, I'll have two equations. I'll have to do them, write the formula twice. So let's start with the x formula. Okay, so first let's get dl dq, okay, which is diff of L with respect to, sorry, let me call this dl dx because I'm doing it for x direction. So that's going to be diff L comma x. So it's very simple. Next, let's do d, this has capital L just to be consistent. dl dx dot. So this is going to be this term, which is also pretty simple. It's diff L x dot. Okay, so far so good. Now let's do d dt of this term. So that's going to be d dt, and the way I'm going to denote it is as d dt dl dx dot. Okay, and this is the term which consists of those four parts. So I just have to take that what I wrote down on paper and transfer it here. So that's going to be diff dl dx dot comma x times x dot. Okay, this is the first term involving x. Then I do the same thing for diff dl dx dot comma x dot times x double dot. So that completes two terms. Okay, so if I keep writing here, it's just going to overflow and it's not going to be in view. So what you can do is, and this is a good practice, is to break it into the next line. So I'll write plus. If you want to break it, then you need to put 3 dots. That's just telling MATLAB that you're continuing it to the next line. So now I just need to copy this, copy, paste, and I just need to change this from x to y. Okay, so that's all the hard work I need to do to get all these terms, right? So I finally need to write the equation. So I'll call them EOM for equation 1, EOM 1, and that's going to be d dt dl dx dot, which is this term, which is sitting right here, minus dl dq, which is the first time I wrote down there. So it's going to be dl dx. Okay. Now there is equal to q, and q, I had given q in my write-up. Q is basically fx, where fx was minus c times x dot times square root x dot square plus y dot square. Okay, so where did this come from? C notes. Need to do a similar thing for y. Okay, so this equation is going to be this minus this equals q. What I'll do is I'll move this q to the left side so that I can write equation 1 is equal to 0. So that will be minus f of x, because I moved this to the right. So other way to write this is minus q equals 0, and that's what I'm writing. So this is going to be my EOM. EOM equals this. Okay, and the magic of this is you run this and something is not defined. Yeah, this is incorrect. So this should have been same as dx. Okay, so you get this equation, and if you check this, let's check it with what I derived from class. So this was the equation for the x direction. It was x double dot minus c divided by m x dot square times square root of. So if you look at this, we have, okay, so this technically is equal to 0. And if you move m toward, you divide the whole expression with m, you should get x double dot equals minus c divided by m times this whole thing. So there was a question. Okay, so I guess I cleared that up. Okay, so this checks with nodes. Now you need to do the same thing, but the best part of this is you don't need to rewrite everything. You can just copy paste. Just be careful. So I need to do y now. So this will change, and then y. So now this will be y, this will be y, this will be y, this will be y. You don't have to change other things because those things remain the same. So then this will be y, y, and y, and let's call this EOM2 and run this. And then you get a slightly more complex expression for EOM2. The only difference here is going to be that you see there's an additional mg term figuring out there, which comes in the second equation, if you see this equation, you see there's an mg term. Okay, so this is what I got over here. If you move this term to the right, you have my double dot, which is here, plus mg, which is there. And then you have this term, which when you move to the left side is positive. So that's what you see in the last term. So this is probably an easy way of deriving the equations. You don't have to do the math. Now, I showed you how to do this, but you have to keep track of all this. I'm going to give you a piece of code which you can write, and it will be much, much simpler to derive the equations. Basically, I don't really memorize this. Instead, I'll just copy paste it over here. So that way you can just keep reusing it. I took some pains to write it down first time, but now I'll just start using it. So this is, I would say, method 1, manually defining terms, right? You still have to do all this thing. Here I'm going to basically call a for loop and do it quickly. So method 2 or automation or okay, so in this here, what I do is I actually define q double dot as whatever my degrees of freedom are, x and y, define f, and then I just have a for loop which does it for me. So it's all compact in one place instead of trying to write two expressions like I wrote down here. So only what I need to do now is just check if these equations come out with the same as what I got earlier. So let me run this. And so you'll see that the equations are derived twice, once for, okay, I need to change it slightly. This is EOM1 and EOM2 to make it easy to compare. Well, actually, let's do it this way. This is EOM1. Let me comment this out. Sorry, let me not suppress printing this. So this is EOM1 and this is EOM2. So let me call that EOM1. And that should match up with my EOM in brackets 1, which comes from the method 2. So EOM1. And then EOM2 should match up with EOM in bracket 2. So if they match up, then my derivation is right. So if you look at this is exactly the same. And then if you look at EOM2 with this, you should see that it is also the same. So there is a way of automating your code. And I would actually henceforth not use the manual method, but I just use this method. In fact, I can extend it to any number of joints by just expanding this. So if it's a manipulator with 5 links, this will change to 5 numbers and so on. Okay, is that clear? Any questions?